The realistic environment provided by learning factories at universities gives students the possibility to implement methods that create and optimize work systems through both theory and practical experience. Continuous flow production is one of the most important types of industrial manufacturing concepts. It supports the efficiency of work systems through orientating the production according to the customer tact. The to-be-produced product serves as the foundation for the design of a continuous flow production, in this case, a multi-piece pneumatic cylinder. The individual components are mechanically manufactured and thereafter assembled to the final product. In the assembly system shown, several inefficiencies are obvious. The assembly of the product in batches generates unnecessary stock between the assembly stations. The distribution of the working stations creates inefficient transportation distances. Furthermore, the working stations are unevenly utilized, which leads to unproductive waiting times due to missing material. These types of waste can be optimized through a continuous flow production. First, the individual tasks in the assembly are documented. From this, the assembly plan is generated. Subsequently, the necessary process time for each individual task of the assembly is determined. This can be determined either using an analytical method, such as real-time measurement, or in cases of a new system planning, synthetic methods such as MTM. In addition to value-adding assembly tasks, there are also secondary processing times for handling, checking, and packaging to be considered. The generation of these assembly times serves as the foundation for balancing workloads in the flow production. The determined process time results can be visualized in an operator balance chart. For each of the 5 workers, the steps carried out and their respective task durations are compared. The total sum of all assembly tasks leads to a process duration of 265 seconds. Currently, it is clear to see that the workload is inadequately distributed between the operators until now. Therefore, the customer tact of 60 seconds is not achieved. A large part of the assembly time is composed of non-value-adding activities, such as searching for parts, unpacking, and especially transportation of material between the single workstations. These unproductive activities can be in a large part eliminated through an optimized continuous flow production. The remaining assembly time of 110 seconds per piece divided by the customer tact of 60 seconds generates the required demand of 1.83 workers. Rounded up, 2 operators are needed in this case. The required workload can then be distributed equally between the 2 operators without the customer tact being exceeded. Thereby, the chronological priority relationships between single elements need to be taken into consideration. For example, the packaging of the product can only be carried out after the assembly is completed. Through the use of digital tools in the learning factory, the result of balancing the assembly line can be validated directly in a virtual layout design before the optimized assembly system is physically implemented. With the assistance of assembly simulation, many significant improvements can be visualized, such as the achievement of an even material flow, the avoidance of stock, and the reduction of transportation distances between the working stations. If the simulated assembly layout and the intended tacting have proven to be suitable, they are realized physically in the learning factory. Workstations are consolidated in an assembly line. Necessary tools and fixtures are installed. The U-shaped line is particularly favorable as it allows the only 2 workers operate the entire assembly system without having to bridge large distances between the individual workstations. Should the assembly line's capacity to be increased, additional operators can be deployed into the system at any time. If the newly designed work system is now started up, effects of the changes are immediately and clearly evident. The material is staged ready for use and as close as possible to the place of consumption, what effectively helps to reduce non-productive times within the assembly process, for example, for searching and unpacking parts. The reduction of the batch size to just one piece, combined with an even balancing of the working steps, induces that components are further processed directly and no intermediate stocks are piling up between the individual stations. Necessary tools are ideally positioned directly at the operation point. Using roller conveyors, input components can be provided to the assembly line and final products can be channeled out efficiently. In particular, however, optimal capacity utilization of the workforce is approached through the synchronization of work steps, while the material flow is taking place rectified at all times. In addition to the qualification and flow production, innovative learning factories also cover manufacturing organization, workplace and work system design, design of material staging systems, resource efficiency, and the reduction of planning times through the use of simulations and virtual engineering tools. Network learning factories can be seen as an indispensable element in the qualification of tomorrow's professionals and engineers. They deliver an elementary contribution to the expansion of our industry's competitiveness and thus are also crucial for the preservation of economic prosperity in Europe.